Hey everyone, welcome back to the channel. In this video, I'm going to go over half duplex, full duplex, and CSMACD operations. So before getting into CSMACD, we first need to understand the concepts of half and full duplex. Half duplex is when a device waits until no other devices are communicating before it tries to talk. And this is similar to a conversation that you have with somebody. Both of you take turns while the other person talks. So you have always one person that's listening and one person that's talking. With full duplex, the device can send and receive data at the same time. So unlike half duplex, a full duplex device is able to receive and process information while it's also sending information. When Ethernet first came out, it was half duplex, and this effectively meant that only one device could use a cable at a time. This half duplex logic uses an algorithm called CSMACD, which stands for Carrier Sense Multiple Access with Collision Detection. Let's break this down a little bit to make it easier to understand. So the first step in the process is Carrier Sense. This is the process where a device actively listens on the wire to see if any data is being transmitted. Now, if the wire is free, there's a timer that begins, and this is called the interframe gap or the interpacket gap. This time is measured in microseconds, and it's the amount of time that a host waits before it puts any data on the wire. If there's still no data detected by the end of that time period, the host will begin transmitting data onto the wire. If the wire is busy, the device will continue to listen, and once the cable becomes free, it will then begin to send the frame on the wire. Now you may be wondering, if you have multiple devices that try to do this, won't that cause a collision? Yes, it will. And we're going to take a look at what that looks like in a little bit. But for now, let's take a look at multiple access. Unlike other methods, Ethernet allows you to send frames one after another without having to wait. So for example, with other technologies such as token ring, once you put a frame on the wire, you have to wait until that frame circles back to you. And then you can strip that frame off of the wire and release a pulse called a token. And that token then goes to the next host, which allows them to put a frame on the wire. So this token goes from host to host, and that token allows whoever holds it the ability to put a frame on the wire. So you had to wait until that token came all the way back to you before you can transmit another frame. So that's what multiple access references in this regard. You can send multiple frames one after another without having to wait for something such as a token. Now let's take a look at collision detection. When a network interface card is transmitting on an Ethernet cable, it owns that cable. No one else should be talking, it has the full bandwidth of that cable. And this is in contrast to some other technologies like cable internet, for example, where there's other signals that are transmitted on that medium, but it's just happening at different frequencies that you're not listening for. So when a NIC is transmitting, it's also listening at the same time. And no data should be coming back to the host. And if it does, that means a collision occurred. So let's take a look at an example of how this works. So in this scenario, we have a hub, and connected to the hub, we have three computers. Computers A, B, and C. So a hub is a simplistic network device that predates a switch, and it's considered a simple layer 1 device because all it does is it takes any electrical signal that comes into it, and it repeats that out all other ports, except for the one that it was received in on. So in this scenario, if we have host B that is transmitting a frame, it will take that and it will duplicate that to hosts A and C. However, it will not forward it back to host B because that's where the signal came from. So we have host B, and right now host B is communicating on the wire. Now we have host A and C, and they want to communicate as well, but they can't because host B is currently transmitting. So at some point, host B is going to be done, and host A and C are going to realize that. So you may be wondering, how do they know that the host is done communicating? Well, there's some specific rules when it comes to Ethernet that are defined within the specification regarding the spacing of time between the communication of data, the ones and zeros that are physically sent on the wire. So Ethernet defines how long the voltage must be on the wire and held there to communicate a 1 or a 0, and also how much time space there is between that and the next voltage change to communicate another 1 or a 0. So the host knows per Ethernet standards after a certain amount of time elapses, that the frame has to be done. Additionally, there's in the 802.3 standard from the IEEE, there's a field that says how long the frame is, and we haven't gotten into that, but we will in another video. So in this scenario, host B is finished with communicating. We have host A and C, and they're going to immediately send a frame onto the wire. Now, remember, they do that because when they initially checked the wire, they saw that host B was already communicating that the wire was in use. So if the wire wasn't in use, you would have that interframe gap timer that begins where the host will listen for an additional time period before they attempt to communicate. However, because they already saw that the wire was in use, once it became available, they both tried to send their frames at the same time. So this is going to result in a collision. So if we pretend here that this looks like a wave, we'll have a wave for A, host A as well. These are going to collide. And the hosts are going to see this because when these waves collide, they're going to hit each other and reverberate back to the source, if you want to think about it that way. So it'll bounce up here and then go back to the source. And this will also happen for host C as well. It'll come up and go back to the source. So this collision is going to be detected by both hosts A and C. So what's going to happen next is both hosts are going to finish transmitting their frames, but they're going to replace the remaining bits of the frame with a sequence of ones and zeros. So for example, if host C was 50% done, then it will fill the rest of the frame, the last 50%, with a bunch of ones and zeros. And this is referred to as a jam signal. And this host will do the same. So say, for example, this host was only 5% complete. They're going to fill the last 95% with ones and zeros. So once a collision has occurred and you've completed your jam signal, you need to wait before you transmit again. A random back-off timer dictates how long a host needs to wait from after a collision until they can transmit again. And this timer is different for every host. Now, you don't need to know this for the CCNA, but how this works is by using a truncated binary exponential backoff algorithm. And this backoff time is determined by selecting a random time between 0 and 2 to the power of C minus 1. And C in this scenario represents the attempts that the host has made at trying to transmit that frame. So if we have host A, for example, and they have attempted to send that frame only once, this would be 2 to the power of 1 minus 1, which equals 1. Whereas if we have host C over here, and maybe this is their third attempt at trying to transmit this frame, it'll be 2 to the power of 3 minus 1, which equals 7. So more than likely in this case, host A is going to end up retransmitting first because they're going to be selecting a random value between 0 and 1 versus host C that's selecting a random value from 0 to 7. And it should also be noted that C is limited to a maximum value of 10. So if there's a collision that still happens to occur after the 10th attempt of sending that frame is then discarded, and the higher level protocols such as TCP would have to try and retransmit the lost data. If you have any questions about what was covered, please leave a comment below. And if you enjoy these tutorials and want to support my work, please like this video and share it with others. If you have the means, you can contribute to my Patreon or leave a tip in my jar. Be sure to subscribe to stay updated on my latest content, and thank you all for watching.